Hello there. Greetings from Ravichandran Mountain Path Academy. Welcome to this session number 7. Today we'll discuss concept on autocorrelation and partial autocorrelation related to ARIMA model. So just want to recollect what you discussed in the earlier session. So in the earlier session we discussed an introduction to ARIMA model, what is an ARIMA model, and what is the importance of ARIMA model in time series forecasting. What are the components of ARIMA model? The AR component, autoregressive component, the MA component, the moving average component, the integrated, nothing but the differentiating the non-stationary into a stationary series. Last session we discussed what is stationarity in time series data, how to deduct stationarity and non-stationarity using in Excel simple mean as well as a ADF augmented Dickey-Fuller test, and also through visualization. Now, and how to transform a non-stationary data into a stationary data by using differentiation. We discussed the last two sessions, and if you have not watched, please watch. And today we are going to discuss what is correlation, why it matters. Then what is correlation to autocorrelation. Then what is autocorrelation and how do you look into autocorrelation in Excel in Correlogram? And what is partial autocorrelation, PACF? How do you look at the plot? And how do you read ACF to PCF together? And how to choose a ARIMA model PDQ? Let's quickly look into what is a correlation. Correlation, all of us knows measures how strongly the two variables x, y move together. So it denotes that if it is correlation is positive, that means the two variables move together. If it is negative, one rises, the other falls. It also provides a correlation, the ranges from -1 to +1. It provides a strength. So how it is a +1 means is a perfectly linear link, or -1 is also 0 means no linear relationship. So it's basically a linear relationship. The Pearson R correlation x, y in Excel. So returns the R, it provides a linear correlation coefficient. And what is autocorrelation? Autocorrelation applies the same principle. Here we are not discussing x, y. So we are discussing what is called the same series with its own past value. So that means y is a series of data, yt is a series of data today, and yt -1. So we are going to look into what is autocorrelation. What it measures how strongly a time series is related its own past. Now, past means we are using lag values. Partial autocorrelation measures the direct relation after removing the effect of the in-between lags. So these two important ACF and autocorrelation, partial autocorrelation are important tools to identify the ARIMA model type or ARIMA model order. Let's quickly go and look into autocorrelation. Autocorrelation is a correlation variable with its own past values. In simple terms, it tells you whether your current data points have got related to the earlier data. Let's take an example here. Let's take the correlation as of now today. What is the data? You want to calculate the yesterday's value, you have to take a lag value. So in Excel we can easily do it. So then we can calculate if the correlation is 0.9, that means today's value has got a direct relationship of 0.90. So we can see the effect strength, whether it is a negative, positive or 0. So autocorrelation measures how strongly the time series is related to its own past. So all of us knows time series, time-stamped data. So partial autocorrelation measures the direct relationship. That's what it. Let's look at the correlogram autocorrelation. Here we have taken about 10 lakhs. We have measured the correlation. You can see that as soon as you're looking at that correlation, you can see it is slowly coming down. So and that means and the past values at lakh 10, the correlation is very less. So that means it is a slow fading process. And sometimes we can also sharp drop to 0. So how we are going to use the ACF plot, ACF values in deciding what is called the ARIMA model. We are going to use. So how ACF is going to decide the moving average component in the ARIMA model. Before that, ACF can also be used to and deduct whether data is stationary or not. If a original data, I have created original data, the correlogram, you can see that a slow decay, it shows the original data as non-stationary. So what you do, you differentiate, you take differentiation 1, you can see that the slow decay is completely gone. Now you have got only one lag which is outside the cutoff point. So we can see that stationary data will not have a slow decay, whereas a non-stationary data will have a autocorrelation slow decay. So that means the autocorrelation also helps you to understand whether whether a series is stationary or not. And why it is so important? First and foremost, autocorrelation helps to find out the MA order type. What is a Q? What is MAQ? That means whether it is are you going to calculate, are you going to use one lagged error values, estimated error values, or two lagged error values. So that means that is very important. So the second important thing is to detect stationality, as you just now saw. Third is check the residuals. So after a good ARIMA model, where it leaves the correlation of the residuals becomes close to 0. The autocorrelation is 0. Now, if the residual autocorrelation shows spikes, then the model is missing something. So after doing everything, you do the final analysis on this one. So this is very important. So the meaning of the positive and the negative autocorrelation. If the autocorrelation is positive, the high values are going to be followed by high values, and low values are going to be followed by low values. If it has got a negative correlation, high values will be followed by low values will be followed by high values. If the zero correlation, autocorrelation, then the series may represent a random noise. So how are you going to do the autocorrelation? Calculate. First we have to calculate lag 1, lag 2, lag 3. So creation of lag is important. So what is lag 1? It compares today's data with yesterday. Lag 2, it compares today's data with the 2 periods back. Lag 3 means compare today's value with 3 periods back. So that is the purpose of creating lag, which is very important, essential in modeling, in ARIMA model. So look at this diagram of autocorrelation factor. You can see that it is a little bit of up and down. So you can see 0.9 at lag 1 minus 0.90 plus 0.784 minus 0.65. So this kind of oscillation. So whenever you see an oscillation autocorrelation or correlogram, we can see that this pattern can be observed mostly in financial data, especially in its mean reverting spreads and inventory cycles and interest rate cycles. So whenever you see what is called an oscillating and autocorrelation and picture, and we can always say it does not have an MA signature. MA, that means we have to test whether it has got an AR signature or not, autoregressive. Then we have to use it. So first, as soon as you see the oscillation, we can say the model is not, there is no MA signature. Now let's look at this diagram, this autocorrelogram. See, it is slowly coming down, goes down, then it goes up. So again, this picture does not look like an MA. So this does not look a moving average. So what is the requirement for a moving average? The question. So it should cut off sharply after lag Q, then rest of the autocorrelation, different lags to stay within the band, or it should go to 0. So that means when this is not an MA type. So this is not an MA type. So mostly this kind of oscillating thing comes in what is called seasonal and time series data, where we can use ARIMA model, which we discuss later. So what is an important core rule requirement for a MAQ? You should cut off after lag Q. That means when you say cut off, spikes and up to lag Q, then suddenly drops to 0, or it should stay within the confidence band. Confidence band is decided by 1.96 divided by square root of n. Now, so in a moving average Q model, if you say MA1 model, then you should cut off after lag Q, after lag 1. That means we can use a term that means epsilon, and that is today's error, plus theta 1 into epsilon, that is yesterday's error. And Or if it is a MA2 model, we can say epsilon plus theta 1 into epsilon T1 minus 1, theta 2 into epsilon T minus 2, like that. Now after that, we can say there is no correlation between the other lags. That means we can assume that correlation is 0, and that means roughly we can assume that. Look at the MA1 and MA2 model examples. So you can see that the autocorrelation cuts off after lag 1 in the first one. The second one, and there are two lags. That is a correlation at lag 1 is above the cutoff, correlation lag 2 above the cutoff. So that means it cuts off after lag 2. So straight away we can decide this particular thing represents an MA2 type, and so we can discuss that now. So there are we have to look into not only the MA type, we have to look into what is called the partial autocorrelation as well. So we should know how to read it. So for MAQ, the rule is simple. The autocorrelation should cut off sharply, and the rest of the correlation, the lag, should stay within the band. That is an important requirement. Okay. Now let's go into partial autocorrelation. What is partial autocorrelation, PACF? So autocorrelation measures the total relation between the past values, whereas partial autocorrelation, direct relation between the time series data and the lagged values after we remove the effect of the shorter lags, that means in between lags. So that means it measures the direct, it's just a kind of a regression. So we have to use a regress, that means what is the current value, we can call it as YT or WT. YT, and with regard to the then how do you do it? We have to use and regress each term, but it's very difficult. So we're going to use simple Linus function in Excel to calculate. So partial autocorrelation is basically, you should know that it measures the direct relationship and of the time series with its own lagged values after removing the effect of the intervening lags. That's an important note. So what is a PACF is directly linked between YT and YT minus K after stripping out the in-between lags. So we discuss autocorrelation includes a chain. That means when you measure autocorrelation between lag 1 and 2 or lag 1 and 3 or lag 1 and 4, it reflects actually an indirect relationship. That means it gives you a total relationship, whereas a partial removes the effect in the in-between. How are you going to calculate partial autocorrelation? We use a regression on YT minus 1, YT minus 2 up to YT minus K. That means the coefficient of the last term is a partial autocorrelation at the lag K. In Excel it is very easy to calculate. So technically you can see that after removing after differencing we get the stationary data. Then we can see the partial autocorrelation directly measures what is called so the relation between YT and YT minus K. Now, so what are the important takeaway from partial? See, it measures the direct, it's a direct measure. What is the purpose? Purpose is to identify the AR order. What is the purpose of the autocorrelation? It measures the MA order. And so partial autocorrelation measures the AR order, and then autocorrelation measures the MA order. Sharp cutoff order. So if there is significant, that means we have to look into how you are going to read both these things together. How you are going to read ACF and these two together. So before we discuss that, and we let us quickly go into an Excel and look into some. So I got some 3 data of model. So let's look into how we are going to calculate what is called a correlation, and that is a simple ACF and PACF. And let's quickly go here. Now this my data. This data is my original data and YT. Okay, this is my original data. Now I'm going, since I'm assuming this data is actually, yes, it has got a trend. We can see the original data. I'm differentiating to make it a little bit of a stationary. So I'm just differencing. So how are you going to difference? So we'll take today's value minus yesterday's value. So we got what is called, first we differentiate. So now this original time series data is transformed into what is called and from YT we are transformed to a difference series. Now I want to take lag. How many lags I need to take? So roughly you can, there is no hard and fast rule. So roughly I will take square root of 50 up and so roughly around 6 or 7 lags I will take. So how do you take lag values? In Excel, offset this comma 0 comma 0. So we will take a control C, copy it across, then drag it down. Now we got what is called different lags of data. So you can remove that and what is called the zeros, and so now we can calculate first and what is called our autocorrelation. So autocorrelation is simple Pearson correlation. We can say correlation and between my and this data, the transformed differentiated data, comma, and this one, the lagged differentiated data. So we got the correlation for the first lag. Similarly, so we can also calculate the one by one correlation for this one. Okay, and for the second one, dropped one comma, then we will take this individual data. Now we got the lag of the second one. Similarly, we have to take and the correlation of what is called the third one. Third one is this one. We have to drop one row down, and now we will take the correlation of this. So simple correlation. There is no big magic here. Now fourth one, again we will drop one more row down and a comma and take the fourth and lag data. So we are calculating and this is the correlation. Okay. Now okay, now the fifth one, this is the fourth one. Hope I'm doing the correct one. This is the third one, and fourth one, this is the fourth one, and this is the correlation of the fourth lag. Now then the fifth one, comma. So this is the correlation, the fifth one. Sixth one, the last one, this one, comma, this one. This is how we can calculate the autocorrelation. So we can also look at the plot. Actually, you can see control C. So you can see, look at the autocorrelation. You can see that slowly and it fades off before, but we do not know, and we have to create a few more things and observe. We have to now first like the partial autocorrelation. How do you get? So you can use a simple. So use a shortcut on regression, index linest. Then we will calculate this one. Okay, comma, and this one, comma, true, comma, true, bracket close, 1, comma 1. So we will calculate what is called the partial autocorrelation. IMS index linest. I put extra one. That's it. Okay, and so you got that what is called a partial autocorrelation. Similarly, and what you can do is if you want to do it quickly, so is going to be there. First is this last row, it is going to be this one, that is going to be constant. Then this one and C is going to be there. So we'll freeze that. Now control C, control V, and now let's look into it. So we have to take that and this one, and now we got this one. So we can see that this is how we can do it. And the next one, and let me just freeze this one also, and this shift $, so that So Control C, Control V. So just want to do it quickly so that we just simply drag this one. So similarly again Control C, Control V. So autocorrelation, you have to take the entire thing. Now for the fourth one, you have to take similarly the fifth one, and you just simply take that one, and again we'll take this one. Now this is how we can track. So now we can see that we have taken partial autocorrelation. Now how do you calculate what is the cutoff? First we'll take the count of the difference variable. Then we'll take the band is nothing but 1.96 divided by square root of n. So this is your and cutoff. Okay. Now we are going to calculate what is called the lower boundary and the upper boundary. We will calculate the lower boundary and the upper boundary. How do you calculate? The lower boundary is minus this one, function f4. This is going to be the same thing. Similarly, this one we will put freeze this one. So copy the lower boundary and upper boundary. Now, so we will just look at the Correlogram here in pure graph. So this one. So now what I'm going to do is, and this one is a cutoff, so convert this one into line graph. Convert this one into line. Similarly, this one is a upper cutoff. So again convert this, change the chart into some line. So now I'll copy this so that you can differentiate between a ACF. So now I'll remove the PACF here. Now I'll remove the ACF here. Now you can see this is your autocorrelation graph. This is your partial autocorrelation graph. Now as you discussed, the partial autocorrelation represents what is called the autoregression AR process. This ACF represents what is called the MA process. Now look at this diagram here. What is the first thing? The ACF tails off. It slowly tails off, and that means so you can even look at that values also, you can see that. Similarly, look at the PACF. PACF, you can see that and it cuts off after lag 1. That means we can say that it is an AR model. PACF represent. So that means and you can see that the PACF cuts off after lag 1. That means it is what is called AR1 model. Now whether it is a MEA model, we have to look into ACF. ACF tails off. That means it is not an MEA model. So we can say MEA model is 0. So MEA model is 0, and now then we already have differentiated once. So that means the ARIMA model is a A10100. So next session we will discuss again how we are going to calculate ACF and PACF, how we are going to decide on other type of ARIMA model, and thank you for watching.